right, get ready to dive deep into the world of machine learning. For engineers specifically, we're going to explore how machines can learn from data and solve those complex engineering problems that you might be facing every day.
It's a fast-growing field,
Hmm.
and it holds so much power, So we're going to break down these complex problems into bite-sized concepts, starting with the fundamentals, obviously, and then work our way through some powerful algorithms that are changing how engineers approach design and problem solving.
Okay, so since we're starting with the fundamentals, you know how we always hear AI and machine learning used kind of interchangeably. What's the real difference between the two?
Yeah, that's a really common point of confusion. Artificial intelligence, AI, that's the broader idea. It's about machines that are trying to mimic human intelligence. And then you have machine learning, or ML, which is actually a subset of AI, where computers they learn from the data without being explicitly programmed.
Oh, okay. So instead of a programmer giving the computer like a very specific set of instructions, we're basically feeding it data and letting it figure things out on its own.
Exactly. Think about spam filtering. Instead of a programmer having to write like thousands of rules to identify spam, machine learning algorithms, they can analyze tons and tons of emails that are already labeled as spam or not spam. And the algorithm, it learns from these examples, it picks up on those patterns, and then it can predict if a new email is spam or not.
So it's all about the data. And speaking of data, I see our outline mentions big data. What exactly makes big data so big?
So that's a very key concept in machine learning, and it boils down to the 5 V's: volume, variety, velocity, value, and veracity.
5 V's. Break those down a bit for me.
Okay, so let's start with volume. We're talking massive amounts of data, way beyond what traditional databases can even handle. Think about social networks, right? Generating terabytes of data every single day. And then you have variety. We're not just dealing with numbers and spreadsheets anymore. Big data includes like text, images, videos, sensor readings, you name it.
Wow.
And then there's velocity, which is the speed at which data is generated and the speed at which it needs to be processed. Think of financial markets. They rely on real-time data to make decisions in like fractions of a second.
Okay, this is starting to sound a little overwhelming, to be honest. How can engineers actually use all of this data?
Well, that's where value comes in. What insights can we extract from all this data? So for example, e-commerce companies analyze customer data to recommend products and personalize the shopping experience. And then finally, we have to make sure that the data is actually accurate and trustworthy. That's veracity. Because unreliable data will obviously lead to unreliable results.
So big data is powerful, but you got to know how to use it.
Yeah.
Now, before we get to algorithms, the outline mentions design of experiments. So I'm guessing it's not as simple as just gathering whatever data we can get our hands on.
You are absolutely right. Design of experiments, or DOE, is crucial. It's all about planning, how to collect data efficiently, and make sure it's relevant, to the problem we're trying to solve.
So can you give me a real world example? How would DOE apply in engineering?
Yeah, so imagine you're testing a new car's braking system. You could just slam on the brakes a bunch of times, but that's not very scientific, is it? DOE helps you design a structured experiment where you're thinking about things like speed, road conditions, and temperature. That way you're getting the right data to evaluate the braking system's performance.
Oh, okay. So DOE is kind of like having a plan, a roadmap. So you're collecting the right data in a structured way. Okay. Now let's get into machine learning algorithms. The outline dives into supervised and unsupervised learning. What's the difference?
So supervised learning is it's like having a teacher guiding the whole process. We give the algorithm labeled data. That means each input has the correct output. So the algorithm learns from these examples to predict outputs for new inputs.
So it's almost like giving the algorithm a set of flashcards to study from.
Exactly.
What about unsupervised? No flashcards?
No flashcards there. In unsupervised learning, we give the algorithm unlabeled data, and it has to figure out the patterns and the relationships without any guidance.
So it's more about finding like hidden structures within the data. Okay, let's get into some specific algorithms. We'll start with the supervised learning. First on the list is linear regression. What is that all about?
Linear regression, one of the most fundamental algorithms in ML. It predicts a continuous output variable based on one or more input variables. Linear basically means we're assuming a straight line relationship between those inputs and outputs.
So like predicting house prices based on things like square footage, number of bedrooms, location, stuff like that.
Yeah, exactly. So the algorithm, it learns that relationship between the features, like square footage, and the price, by adjusting weights. It's basically finding the line that minimizes the error between the predicted price and the actual price. And this is often done through what's called gradient descent.
Gradient descent. So if I'm understanding this correctly, it's like trying to find the lowest point in a valley. You take small steps downhill, always moving in the direction of the steepest descent.
Yeah, that's a good way to visualize it. It's iteratively adjusting the model parameters until it finds the values that minimize the error.
Okay, so linear regression, it works when there's that straight line relationship, but what if it's more complex than that?
Well, sometimes we can still use linear regression, but we introduce what are called higher order polynomial terms. Essentially, we're bending the line to fit the data better. You can think of it like fitting a curve instead of a straight line.
Ah, that's a neat trick. But I imagine using more complex terms, you could run into some issues, right?
Right. One potential issue is overfitting. And this is where the model becomes too complex and starts to just memorize the training data instead of learning those underlying patterns. So when you present it with new data, it won't do very well.
So it's almost like the model gets too specific to that training data and can't handle new situations. How do you prevent overfitting?
Well, there's a couple of techniques. One is called regularization, which basically penalizes overly complex models. Another is just using more training data. If you give the model more examples, it'll be less likely to
So
memorize.
linear regression, great tool, but you got to be careful about overfitting. Now, what about logistic regression? It sounds similar, but I'm guessing it has a different purpose.
You got it. So while linear regression predicts a continuous output, logistic regression is used for binary classification. That means the output is one of two categories.
So like classifying emails as spam or not spam.
Exactly. Or predicting if a loan application will be approved or denied. It uses a function called the sigmoid function to transform the output into a probability score between 0 and 1. So this score basically represents the model's confidence in predicting the right category.
So instead of just a straight numerical prediction, you get a probability,
Mm.
which can be, more useful for making decisions. How do you actually evaluate logistic regression?
Well, one common tool is the confusion matrix. It shows you the counts of true positives, true negatives, false positives, and false negatives. And from that, we can calculate metrics like precision, recall, and the F1 score. These give us different perspectives on the model's performance.
It's like getting a report card, highlighting the model's strengths and weaknesses. So we've talked about linear and logistic regression, and they both assume this kind of linear relationship between the inputs and outputs. Next on the list is decision trees, which sounds like a totally different approach.
Yeah, you're right. Decision trees are very powerful, and they can handle both linear and nonlinear relationships. They work by recursively splitting the data based on different attributes or features, creating a tree-like structure.
Can you walk me through an example? Let's say we're trying to predict if someone will play tennis based on the weather outlook, temperature, humidity, and wind. How would a decision tree, how would it tackle this problem?
Sure. A decision tree might start by splitting the data based on the outlook. If it's overcast, the tree might just predict that the person will play tennis because, overcast conditions are usually favorable. But if the outlook is like sunny or rainy, the tree might split the data further based on other attributes like humidity or wind to make a more refined prediction. It's basically creating a series of if-then-else rules.
So it's like asking a series of questions to get to a prediction. What are some key concepts when it comes to decision trees?
One important concept is information gain. This basically measures how well an attribute separates the data based on that target variable. So attributes with high information gain are usually chosen to split the data. Another concept is the Gimani index. This measures the impurity of a node in the tree. So nodes with a low Gimani index are considered more pure, because they contain mostly data points from a single class.
So it's all about finding those attributes that best divide the data into those categories. I imagine, though, just like with the other algorithms, decision trees can also overfit.
You're catching on. If we let the tree grow too deep, it might perfectly classify the training data but perform poorly on new data. So to prevent this, we can use techniques like pruning, where we're essentially removing branches that don't really add much predictive power.
So it's like trimming a tree to make it healthier, more robust. What I like about decision trees is you can easily understand how the model is making its decisions. That's not always the case with some of the more complex algorithms like the next one on our list, neural networks. Those are often described as like mimicking the human brain.
Right. Neural networks are a a really powerful class of algorithms inspired by the structure and function of the human brain. They're made up of these interconnected nodes or neurons that are organized in layers. And these networks, they can learn very complex patterns and relationships, making them suitable for things like image recognition and natural language processing.
Taking inspiration from the most complex organ in the human body. That's pretty amazing. So let's break down the structure of a neural network a little bit. What are these neurons all about?
So each neuron, it receives input from other neurons, performs a simple calculation, and then it outputs a signal to other neurons. The connections between the neurons have weights associated with them, and these weights are adjusted during training to kind of optimize the network's performance.
So it's almost like this network of signals flowing through the network with the weights acting as like volume knobs controlling the strength of those connections. Now, our outline mentions perceptrons. They're like the building blocks of neural networks. What are those exactly?
Yeah, perceptrons are like the simplest type of artificial neuron. They take a set of inputs, multiply each input by its corresponding weight, sum up those weighted inputs, and then apply an activation function to produce the output. And that activation function is really important because it introduces nonlinearity, which allows the network to learn more complex patterns.
So they're like mini decision makers within the network. But how does a neural network actually learn? How do those weights get adjusted?
One of the most common algorithms is called backpropagation. It uses gradient descent to adjust the weights in the network. So it calculates how much each weight contributes to the error in the network's output, and then it updates the weights to try to reduce that error.
So it's like a feedback loop where the network's constantly learning from its mistakes. But neural networks can get incredibly complex. How do engineers manage all of that complexity?
Well, that's where network architecture comes in. Depending on the task at hand, engineers design networks with different structures and layers. For instance, convolutional neural networks, or CNNs, are specifically designed for image processing. They use convolutional layers to extract features from images, and then pooling layers to reduce the spatial dimensions. Then fully connected layers combine those features and make predictions.
So it's almost like you have a specialized team of neurons, each with its own specific role in processing the data. Now, our outline mentions recurrent neural networks, or RNNs. These sound particularly relevant to engineering applications.
Yeah, RNNs are designed for processing sequential data, like time series data or natural language. So they have this ability to remember information from previous steps, which makes them suitable for things like weather forecasting or speech recognition.
It's like giving the network a memory. Wow. Neural networks are a powerful tool for tackling those complex engineering problems.
Oh,
But they're not without your challenges, right?
definitely. Training them can be computationally expensive. It requires lots of data, and they can also overfit. So you need to think about regularization techniques and the quality of your training data.
So it's a trade-off between that power and complexity. But with the right approach, they can open up some really incredible possibilities. Well, that wraps up our dive into supervised learning algorithms.
Next, we'll explore the fascinating world of unsupervised learning, where algorithms uncover hidden patterns without any guidance. Welcome back to our deep dive into machine learning for engineers.
So far, we've been talking about algorithms where you have labeled data, the input and the desired output. But what happens when you don't have those labels? That's where unsupervised learning comes in, right?
Exactly. Unsupervised learning is all about uncovering hidden patterns in data without any labels or target variables. Think of it like exploring a new city without a map, discovering hidden gems, and you're understanding the structure organically.
So we're sending these algorithms out as explorers. What are some of the tools that they have in their toolkit?
Get ready to unravel the mysteries of clustering and dimensionality reduction.
Ooh, those sound intriguing. Let's start with clustering. I see K nearest neighbors, KNN, on our list. Is that the same KNN that's used in supervised learning?
You're right. KNN can be used for both supervised and unsupervised learning. In the context of unsupervised learning, KNN is often used for clustering. That's grouping similar data points together based on their proximity.
So how does that actually work?
Yeah.
It's all about finding the neighbors.
Imagine you have a scatter plot of data points, right? Let's say these data points represent different types of cars. KNN looks at each data point, and it identifies its K newest neighbors based on a distance metric, something like Euclidean distance. And data points that are close together in this space are considered similar and grouped into the same cluster.
So you could group cars
Yeah.
with simple features like engine size, fuel efficiency, and price into different categories. But how do you actually choose the right value for K? That seems important.
It is absolutely important, and choosing the right value for K often involves some experimentation. It depends on the specific data set. A small K might lead to more fragmented clusters, while a larger K could give you more general
So
clusters.
it's like a balancing act. You have to find the right level of detail. Are there any other things you need to watch out for with KNN?
Well, K&N can be sensitive to the scale of the features. If one feature has a much larger range than others, it can dominate the distance calculations and kind of distort the clusters. So normalization is important. You need to scale all the features to a similar range.
So it's like making sure all the features are on an equal playing field. So KNN is one approach to clustering. What are some other techniques out there?
Another popular one is K-means clustering, and this aims to partition the data into K distinct clusters. So unlike KNN, which just groups data points based on proximity, K-means tries to find the best clusters by minimizing the distance between data points and their cluster centers.
So it's less about just being close and more about optimizing the clusters themselves.
Mhm.
How does it actually find those optimal clusters?
It's an iterative process. K-means starts by randomly assigning K cluster centers. Then it assigns each data point to its closest cluster center and recalculates those centers based on the mean of all the data points in each cluster. And this process just repeats until the clusters stabilize and they don't change significantly.
It's almost like finding the center of gravity for each cluster. But just like choosing K in KNN, how do you decide on the right number of clusters for K-means?
That's a great question. And again, it often depends on the data set and the goals of the analysis. One approach is to use what's called the elbow method.
Hmm.
You plot the within cluster sum of squares for different values of K, and you look for the elbow point on the plot. This often suggests a reasonable number of clusters.
So you're looking for that sweet spot where adding more clusters doesn't really give you that much more information. Now, both KNN and K-means, they seem to assume that clusters are kind of spherical and well separated.
Mm.
What if the data is more complex than that?
You're right. Those algorithms do have limitations. If your data is more complex, you might need something like Gaussian mixture models or GMMs, and this is a more flexible technique that can handle clusters with different shapes and densities.
Okay, so that makes sense. GMMs sound pretty powerful, but probably also more complex to work with.
They do require more sophisticated calculations, but they can be very helpful when you're dealing with, real world data that doesn't always fit into those neat little boxes.
Now, clustering is all about grouping similar data points together. What about dimensionality reduction? That almost sounds like the opposite.
You're right. Dimensionality reduction is about simplifying data by reducing the number of features, but while trying to preserve as much important information as possible.
So why would we want to reduce the dimensions of your data? What's the benefit there?
Well, think about it this way. Sometimes you have a lot of features, but not all of them are equally important, right? Some might be redundant, some might even be irrelevant. And high-dimensional data can be very computationally expensive to process. And it can also lead to issues like the curse of dimensionality.
Curse of dimensionality. That sounds ominous.
It basically means that as the number of features increases, the data points become increasingly sparse, and the distances between them become less meaningful. So dimensionality reduction can help with this. It can also improve the performance of other machine learning algorithms by getting rid of those unnecessary features.
It's like decluttering your data. Now, I see principal component analysis, or PCA, on our list.
Mhm.
How does PCA actually work?
PCA is a popular technique that finds the directions of greatest variance in the data, and then it projects the data onto those principal components. This reduces the dimensionality while trying to keep as much of that original variance as possible.
Okay, so can you give me a real-world example? Let's say you have data on height, weight, and shoe size for a group of people. How would PCA simplify that data?
Okay, so PCA might discover that most of the variation in the data is captured by a single principal component that combines height and weight. This suggests that height and weight are highly correlated, and you can essentially represent those two features with a single combined feature.
So it's like finding this hidden pattern in the data, this single factor that explains a lot of the variation. Does PCA have any limitations?
Like all techniques, PCA has its limitations. It assumes that the data is linearly related. So if the relationships between features are nonlinear, then PCA might not be the best choice. And while it aims to minimize information loss, there will always be some loss when you reduce the dimensions.
Seems like there's always this trade-off between complexity and the amount of information that you can retain. But when used correctly, dimensionality reduction can make the data a lot easier to work with. So we've covered clustering and dimensionality reduction. Those are two powerful tools in the unsupervised learning toolkit. What's next on our machine learning journey?
Next, we'll move on to reinforcement learning, where agents learn through trial and error to maximize rewards. Get ready for some fascinating applications in robotics and control systems.
Welcome back. We've covered supervised and unsupervised learning, and now it's time to dive into reinforcement learning. It sounds a bit like we're like training a pet,
Yeah.
with rewards and penalties.
Yeah, that's actually a good analogy. In reinforcement learning, or RL, we train what are called agents to make decisions in an environment to maximize their cumulative reward. So think of like a robot learning to navigate a maze. The robot is our agent. It explores the maze by taking actions, and it receives rewards for reaching certain checkpoints or penalties for, hitting obstacles. Over time, it learns the best path to get the most rewards.
So it's all about trial and error, kind of like a video game character learning how to level up. Now, I see something called Markov decision processes, or MDPs, on our list.
Yeah.
What role do those play in RL?
MDPs are a mathematical framework for modeling these types of decision-making problems. They give us a structured way to represent the environment, the agent's actions, and the rewards or penalties associated with those actions.
So it's like defining the rules of the game for the agent. What are the key components of an MDP?
An MDP has a set of states which represent the different situations the agent can be in. Then you have actions, which are the choices the agent can make in each state. And then transitions, which describe how the agent moves from one state to another based on his actions, often with some element of randomness involved. And finally, you have rewards, which tell you how desirable each state or action is.
Okay, so going back to the robot in the maze, the layout of the maze would be the states, right?
Mm-hmm.
And moving forward, backward, left, or right, those are the actions. Bumping into a wall might be a penalty, while reaching a checkpoint gives you a reward. And the robot needs to figure out the sequence of actions that leads to the biggest total reward.
Exactly. And the robot strategy for choosing actions is called a policy. And in RL, our goal is to find the optimal policy, the one that maximizes the expected reward over time.
So it's like finding the best strategy to win the game. What are some of the ways that we can actually find that optimal policy?
Well, there are a couple of different approaches. One popular algorithm is called Q-learning. This is a model-free RL algorithm, meaning the agent doesn't need a complete understanding of the environment. Instead, it learns an action value function called the Q function, which estimates the expected cumulative reward for taking a specific action in a given state.
So it's learning as it goes, kind of like building a map of the maze in its head based on experience.
Yeah.
How does the Q function actually get updated?
It's an iterative process.
Yeah.
The agent takes an action, sees the reward and the new state, and then updates its Q value for that state action pair based on what it just learned.
So it's keeping track of how successful each action was in each state. Now, this all sounds computationally intensive, especially for complex environments.
Yeah, you're right. One way to make it more efficient is to use what's called function approximation, where a neural network actually represents the Q function instead of a giant table.
Yeah.
This helps the agent generalize its learning to unseen states and actions.
So neural networks can help make RL more powerful, but RL isn't just about robots and mazes, right? What are some real-world applications?
Yeah, RL is being used in all sorts of fields, from robotics and control systems to finance and healthcare. It's being used to optimize traffic light systems, personalize treatments for patients, and even develop self-driving cars.
Those are some pretty impressive applications. It sounds like RL could revolutionize a lot of industries.
It definitely has that potential, but it's also a relatively young field. There's a lot of ongoing research.
So what are some of the open questions or challenges that researchers are working on?
One of the biggest challenges is developing algorithms that can learn efficiently in very complex environments. Another is making sure that RL agents are safe and robust in real-world applications where mistakes can have serious consequences.
It's like making sure that robot in our maze doesn't accidentally walk off a cliff.
Exactly. But with continued research and innovation, RL really has the potential to change the way we solve all kinds of problems.
Well, this has been a fascinating journey through the world of machine learning for engineers. We've covered the core concepts, explored some key algorithms, and seen just how powerful these tools can be. It's been great having you as our expert.
Thanks for having me. It's an exciting field, and it feels like there's endless possibilities.
That's right. And who knows, maybe one of you listening will be the one to develop the next groundbreaking machine learning algorithm. Until then, keep exploring, keep learning, and keep on diving deep.